Kia ora and welcome to video 10 in our series Agile Algebra. In this video we're going to look at a simultaneous equation. The first equation there is just a nice simple linear equation. The second equation there involves the absolute value function. For those who don't know about the absolute value function, it's just an on-off function. It turns negatives into positives and it doesn't do anything to positives. For example, the absolute value of minus 3 is positive 3. Whereas the absolute value of, say, 6 is just 6. It does nothing to positive numbers, but it makes negatives into positives. So when you're solving the simultaneous equation, I guess the only hint I can give you is that you need to consider a case-by-case approach. Give the problem a crack, and then after the video has its intro music, I'll get into the solution. All the best. Okay, the solution to this problem is a fairly quick one. As I mentioned at the outset, we consider a case-by-case approach here. What I mean by that is if x and y are both greater than or equal to 0, then those absolute value symbols around the x and the y do nothing. So we could consider a first case, case 1, if x and y are greater than or equal to 0, then we're actually just solving this problem. Now, if x minus y is greater than or equal to 0, it's like a subcase. If x minus y is greater than or equal to 0, then those symbols do nothing. And we've got x minus y equals 1, and we've got x plus 3y equals 3, the other equation. Solving that simultaneously by subtraction. 4y equals 2, or y is equal to a half. Now, when we've got y is equal to a half, x must equal 3 over 2 to satisfy those equations. And if we just check those, 3 over 2 minus 1 over 2 is 1, and 3 over 2 plus 3 lots of 1 over 2 is 6 over 2, which is 3. So it satisfies those equations. But does it satisfy the original conditions? Well, yes, they're both positive. And is x minus y greater than or equal to 0? Yes. So that is a solution because it's valid, it meets the original conditions. If we look, I cheated and I made a graph on Desmos. And the absolute value equation there, it's just one equation, but it's got many different graphs depending on x and y. So 3 over 2, 1 over 2. Is one of the solutions, and that is there. So we just need to find the other solutions, which we can see easily graphically, but we need to consider a few more cases. So the other subcase, case B, was if x and y are greater than or equal to 0, but x minus y is less than or equal to 0. If that's the case, then those absolute value symbols, the second set, this one here, is actually going to flip that thing around. X minus y, if it's negative, the absolute value of it will be the negative of that negative number. So we'll be dealing with y minus x equals 1. Put together with the other equation, which doesn't change if x and y are both positive or negative. It doesn't really matter because there's no absolute value symbols in that other equation. And if we solve that simultaneously by addition, we get 4y equals 4, y is equal to 1, and if y is 1, x is 0. Now, does this solution meet the original criteria? X minus y is less than or equal to 0. Yes, it's negative, and it also satisfies the original condition that they're both greater than or equal to 0. So yes, that's a valid solution as well. And we've got that solution there, 0, 1. So there are other cases to consider because that was just case 1A and 1B. Case 2 would be if one of them is positive and the other is negative. And this is going to give a contradiction. So if x is greater than 0, or greater than or equal to 0, and y is less than 0. So now the equation becomes the absolute value of x plus y equals 1, because that second absolute value symbol that's around the y, because y is negative, it's going to return the negative of the thing inside it. In other words, a positive number. And then we've got another couple of subcases. Case A, if x plus y is, if they're both greater than 0, greater than equal to 0, then we're solving x plus y equals 1. We just get rid of the absolute value symbols. They don't need they're not needed there. X plus 3y equals 3. Solve that simultaneously by subtraction. 2y equals 2. Y is 1. X is 0. Now that's a solution that we've already got, so we don't need that again, although it does technically fail the original condition of y being negative. We've come out with a y that's positive, so it doesn't meet the criteria for this one, but we already had that as a solution. Second case for this one is if x plus y turns out to be negative, then we're solving negative x plus y equals 1, negative x minus y equals 1, and we're solving that alongside the other equation again, x plus 3y equals 3. Add those equations together, we get 2y equals 4, y is 2, and if y is 2, x is equal to minus 3. Is that possible? Well, in case 2 we were saying x had to be greater than or equal to 0, so it contradicts the original condition, so it's not a solution to the problem in this particular case. However, we are going to come across that soon, that solution again, because it is the last solution that we're trying to spot. Will come up when we get to one of the later cases. Okay, there are two other cases, right? There's case 3, which would be if x is negative and y is greater than or equal to 0, and then case 4 would be if x and y are both negative, and then we've got the subcases of each. So I'm just going to jump straight to the case that we need to consider, which is if x is less than 0 and y is greater than or equal to 0. So that's another case. And then for this particular one, if x is less than 0 and y is greater than or equal to 0, we've got our equation becoming negative x minus y. We can just get rid of the absolute value symbols around the y. Is equal to 1. And then we've got a subcase if those things there are positive. So x minus x minus y is greater than 0, greater than or equal to 0. Which is the same as saying y is less than or equal to minus x. Then the equation, we just get rid of the other absolute value symbols. We're solving minus x minus y equals 1, along with x plus 3y equals 3. Add those equations, 2y equals 4, y is 2, and if y is 2, x is negative 3 again. So we did get that final solution out there, and it does this time satisfy the constraints up here. Okay, x is less than 0 and y is greater than or equal to 0. It also satisfies this condition. The y value is less than or equal to minus x. So that's a solution, and that's the last one. So there are 3 solutions to the problem. The one I just highlighted in green, and these 2 here. Now, I could have solved this in a different way. If I just squared these equations. So, if I took this equation, and if I squared both sides, the absolute value turns negatives into positives, but the squares are going to be the same. So I would get that, technically plus or minus. Okay, both those things can be true. And then if I squared again, I'm going to get x minus 2 lots of the absolute value of x times the absolute value of y plus y. Oopsies, the absolute value of x squared is x squared, and the absolute value of y squared is y squared. And then that equals 1. And then I could move some stuff around. Then I could square both sides again. Now it gets messy. And then I do some more tidying up. And then I remember that my other equation was x equals 3 minus 3y. So I could substitute that in. And if I simplify this out, it's an absolute monstrosity. But if I solve that as a polynomial, I get y is equal to, I get y is equal to 1/2, or y is equal to 1, which is repeated, or y is equal to 2. Okay, and those three y values all have a corresponding x value. X is equal to, actually we don't need to find the x value because the question just said how many ordered pairs were there.